So again, you're going to go to the discussion thread if you do have a problem with the time, which again is in 2 weeks. And what we're going to do today and tomorrow is we're going to finish up stuff. If you go to Blackboard, we're not going to have an official review like we do for the tests and the quizzes, because if you go into Blackboard, there are at least 3, and I think there might be 5 old finals, and you'll see that finals don't really change a lot. So if you look at old finals, you'll see about what they look like. And next Monday, we'll just go over quick questions. So for example, we haven't had the 4, 5, 4, 6 on a quiz, so I might go over those and then go over whichever one you have questions on. Which brings up another thing, which is, I think I said this on Monday. No, I wouldn't have, because we had tests on Monday, thinking of the class, is we are done with quizzes. So I think we had a total of 5. And even though there aren't as many, usually we'd have 6 or 7 or even 8 in a semester. But because obviously things have changed, we don't have as many. But the syllabus said the lowest 2 are dropped, so the lowest 2 are dropped, because basically syllabus is a contract. So you better do well, better have a good grade on the quizzes. Okay. On the other hand, we haven't had a quiz, as I said, in 4, 5, 4, 6. So if you would like, I can do what I did with the quiz right when we went online, which is do a mock quiz that isn't counted for anything, but just you can check to see if you know the material. So would you like me to put up another mock quiz up on 4, 5, 4, 6 for tomorrow? Probably. So I'm answering different things. So 4.7 will start quickly tomorrow, which pretty definitely means it's not in the final, but you'll remind me tomorrow to answer. We're kind of writing the final right now, so we're deciding. All right, so tomorrow, probably not during class time, but sometime in the afternoon, I'll put up a mock quiz for the material on 4, 5, and 4, 6, and 4, 7 if that could be on the final. And I will put up answers to that on Friday. And like the last one, if you want me to, you can email me your solutions and I'll grade it as if it's a quiz. And I'll tell you what you would have gotten, just if you want to know how you did on it and see if you wrote it in a proper manner. Okay, so any questions about then mock quiz final? Okay, so today, obviously, I'm not assuming you did any of the homework. What I'm going to do is start with a couple examples from 4.5. I'll remind you what the formula is that we're using. And then we'll get into 4.6. I think I said last week that the setup in these next 3 sections is similar to the previous 3 sections. So in 4.2, we did basic line integrals, and then 4.3 and 4.4 were cases where we had theorems that we could do it in a simpler manner. 4.5 is base case for flux, and then 4.6 and 4.7 are cases where you can do it in a simpler manner, or at least a different manner. So kind of a similar setup. So as I said, first let me remind you is the dot product of the vector field. So the flux of a vector field V through a surface M is the integral over this surface of the vector field dotted with the normal vector to M. So N is and that's equivalent to the second one, V of R of U of V dotted with the cross products of the two partial derivatives. And this is where parameterization of M, where R of U of V is a parameterization of M. Remember, if you want to think of this as something physical, so you can see what's sort of going on, is you can think of this like a river. V is the flow of the river, and M might be a net. And so we want to know how much water goes through the net in a given time period. So there's the general one. And let's look at an example. And I did a more complicated one on the notes that I'm going to put out on Blackboard, but I'm going to simplify it so hopefully I can actually do it more easily. So here's a vector field. In this case, I will just give you the parameterization. Only little problem is since I just make up something like this, I don't know what that surface looks like, but that is some two-dimensional surface in 3 dimensions. And so I want to find what is the flow of this vector field through this surface. So you can see in some ways it's similar an idea with an extra piece of what we did with the line integrals, which is we're going to put the parameterization into V, and we're going to take the dot product with a normal. The extra piece is first we have to get the normal, which is the cross product of the two partial derivatives. So RU is equal to that. And that. And then the cross product then is, and so I'm trying to fit it in. So since I'm going to be doing this in my head, you're going to double check to make sure I haven't done something silly. Does that look right? Yeah, okay. So there's the cross product. That is a normal vector because remember U is along the tangent plane, RB is along the tangent plane. So if we take the cross product, we get something perpendicular to the surface. And now we put it in. So V goes from 0 to 2, 0 to 1. And now we put the parameterization into our vector space. So x times y x plus y z, and the dot product of that with our normal. So even the simpler one is kind of annoying. You can see it's not actually bad because it's just the dot product is just going to be the 4uv times u squared plus v squared plus the u squared plus v squared times negative 4u. Oh, and that of course shouldn't be 2y. It is 2u. And then minus 4b cubed. So sorry about the mess, but you can see even though it's annoying since I just made it up, it isn't bad. It's just a polynomial u's and v's. So let me say, so someone says, let me look at the middle term. So it is 2u times 2v, which is 4uv. But remember the middle term, you switch the sign. So I think that's right. Oh, the only little thing is I lost. This should be a v, right? Yeah, in some ways, I think it was a v there. I just kind of lost it. So yeah, the middle term should be minus 4uv. And so therefore, that should all be minus 4uv. So this is, in general, how you do it. So you can see it's not necessarily difficult. It's just a bit tedious. The only little thing is, instead of giving you a parameterization, we might surface and ask you to parameterize it. And as usual, there aren't too many that we assume you can do. So for example, you should be able to do cylinders, you should be able to do spheres, you should be able to do things like parts of a plane. There aren't too many. So any questions on this? And we will do, obviously, another one, but so any questions on the basic idea? Right, so another one. And for tests and finals, what we often will do is try to simplify things. So again, we have a vector field. So here's another one. And this is kind of more typical of what we usually do on tests in the final. So here we have a vector field. We want to find the flux through the disk. X squared plus y squared is less than or equal to 4 when z equals 3. So in some ways, for this type of thing, we're checking to see if you remember what we're actually doing, which is we want to take the dot product of the vector field and the normal vector to the surface. And in this case, you should be able to just see what it is. So we shouldn't have to do a parameterization where we put in, get the two partial derivatives and look at the cross product. Because for this disk, what is the normal vector? And in some ways, I can't draw it so it looks nice, but if you think of this, the disk in the 3D, what we have is, if you picture your desk as the XY plane, we have a disk that is parallel to the XY plane and above it. And so therefore, since it's flat, there's just one normal vector, and it is this one. Notice it could also be the one pointing down, which is why I have to put in parentheses that we're looking at the flow going up through the disk. And for the parameterization, because we have to plug that into V, you'll notice we don't need a full one, because I'm going to take the dot product of this with this, which means I don't really care what those two are, because I know when I take the dot product, I'm going to get 0. And the third one, you can see I've made really simple. So the parameterization is something, something, 3. If you're really doing it, since that is a circle, we would have things like r cosine theta and r sine theta, where r goes from 0 to 2 and theta goes from 0 to 2 pi, but we don't need it. And like do the integral for the disk. So if I plug this into here, actually I was a little careless here, which is the reason I don't need these two is because all I need here is, when I plug it into F, all I need is a third one, and the third one just says Z. And I think we had one of these last week. Now we have an integral with just a constant, which we know is going to give us just 9 times the area of, in this case, the disk. Well, of course, the area of the disk is pi r squared, and r is 2. And so therefore I get 36 pi. And that is our flux or flow through that disk. So in some ways, this is fairly typical of test and final questions. It's using the basic idea, but you can skip some of the steps because things simplify. You can read off the normal, so we don't have to look at the cross product. We don't need the full parameterization because in this case, we're only plugging in for the last entry of V, and for that, we just need Z. So any questions on this? And again, if you want to be picturing something, this doesn't really make sense, but if v is the velocity of the river, and in this case we're asking, which really doesn't make sense because we're going up, we're asking how much water flows through that disk. And obviously there's some implied time frame here. So velocity is per second, this is per second. Right. So any questions on this? Okay. So let me do the next one. And what I'll do is bring it into with 4.5. I will, for the first example, which would probably be as far as we'll get, is say how we would do it if we were doing it with the method of 4.5. So this is all part of the theorem. I figure I'll put it separately because this is all mostly saying, except for that last part, saying that it's a nice surface. So it's compact, which means nothing is going off to infinity, and it's closed. It's connected, which means we don't have two separate surfaces. It's all one surface. Piecewise regular, remember, means that the partial derivatives exist and aren't equal to zero, because that would make it messed up, and the closed surface sort of goes with the compact. So the oriented out is the one thing we just assume for the theorem, which is we could ask how much is flowing into our closed set or how much is flowing out. So it doesn't really matter which one we look at, but for the theorem, they're assuming it's looking at the flow out. And that's not supposed to be a partial symbol. That's supposed to be a boundary. It's always a bad choice of symbols for the two, but the boundary symbol looks like the partial derivative symbol. And this is, in some ways, kind of an extension of Green's theorem. And again, we won't try to prove it or say why it is. It says that the flow of F, and I'm not sure why I'm using F instead of V, but why not, of F through the two-dimensional surface boundary of E that is equal to the triple integral of this thing called the divergence over the actual solid E. So E is the solid, boundary E is just the skin of it, or the surface of it. And let me remind you, this was in 4.1. Now we're using it, so I'll remind you that the divergence is this. And as I said, why this works, we're not going to try to prove. So as usual, let's look at an example. But you can see it's sort of like Green's. So Green's is, if you have a line integral, you can say it's equal to a double integral over a region if the path is closed. This is saying if we have a surface that is closed, then instead of doing the flux through the surface, we can do the regular triple integral over the solid. So example. And since the first example, really easy. So given the cube, where x and y and z are all between 0 and 2, okay, so suppose we have that. Then we want to find the flux. And since the theorem assumes that we're looking at the outward orientation, let's start with that one, which is the flow out of the cube. So the divergence theorem says instead of doing the regular flux integral, we can do the triple integral. And for that, we want this thing called the divergence, which is just if I call this P and Q and R, it's the derivative of P with respect to X plus the derivative of Q with respect to Y plus the derivative of R with respect to Z. And the divergence theorem says that the flux over the boundary of E, so here E is the solid cube, whereas the boundary would be just the sides. So the two-dimensional surface. So the divergence theorem says that flow through the two-dimensional cube is equal to this divergence over the solid cube. And you can see in this case, this second one is pretty easy. Since the cube is just x, y, and z, you go from 0 to 2. I just get that. And I should at least do some of these, so I'm going to do it with respect to x first. Which is 18. And since that's now a constant, and it's just going to give the area of the two-dimensional thing, which is just a square. So there's the flow out of the cube. So as I said, you can see it's similar in some sense to the idea of the Green's theorem, which is we take an integral. When we introduce an extra integral, we take it from a flow or a line integral to a more basic and triple integral in this case. And so in this case, this is saying that for this vector flow, stuff is flowing out of the cube. If we were pointing in, the only difference would be we'd be doing the same thing, except we get a negative instead. So obviously, if the flow out is 72, the flow in is negative 72. So here's basic divergence theorem. So any questions on this? Obviously, we have to do more examples, but okay. So let me actually do the same thing. Let's talk about how we would do this using the methods from 4.5. So using 4.5, we would have to parameterize each of the sides. So there are 6 sides to the cube. Let's look at the front first. So in the front, we know that x is equal to 2. And y and z can be whatever you want. So therefore, the parameterization would be 2 and u and v. Where u and v can be anything from 0 to 2. And then we do the same thing we did in the last one. We would plug in, and actually I'm going to start this and then ask you a second question. We'd plug in the parameterization into our vector field, which I have in the last one, which I have to look up. It's, and now before I go on, let me ask, can you tell me what the normal vector is in this case? In other words, am I going to have to take the partial derivatives and take the cross product to get the normal? Or can you just tell me what it is? Right, so it's 2, 0, 0. Really, there's no reason that we need the 2, so I'm just going to say 1, 0, 0. In fact, it should be that because remember, our normal vector should be a unit vector. So I know I don't really need these. So I can put them in to get the parameterization. I don't really need them because I'm going to take the dot product of that with n. So why bother writing anything for the rest of them? So u and v both go from 2, and then we're going to do the dot product of f with the parameterization times the normal vector. And you can see that isn't bad. But this is only one of the 5 sides. So we'd have to do the other 5 sides. So for example, for the back, it would be really simple. So that wouldn't be a really simple one because at the back, x is equal to 0. The normal would be negative 1, 0, 0, but that's not going to matter. Actually, no, I guess it would. The normal vector, negative 1, 0, 0. X is 0, so it would become uv here. And then we'd have to do the 2 sides, and we have to do the top and the bottom. So you can see this obviously is the longer way to do it, even though individually each of the pieces is pretty easy. Yeah, so this one I can actually kind of draw, which is here's the plane. Right, we're just getting the cube. And so you can see the normal vector at the front is just pointing straight out along so perpendicular to the YZ plane. And same type of thing if I looked at the normal vector here, that's perpendicular XZ plane, so that would be 0, 1, 0, and this vector would be 0, 0, 1. So since it's a cube that is oriented with the axes, they're pretty easy to read off. So any questions on this? So let me do one more where there'll be a sort of a follow-up, but I won't actually completely do it. So here's another one. So I take a sphere, I just look at the top half of it, and then to make it so the divergence theorem works, I will close it with a disk at the bottom. So it's a closed upper half sphere. So since it's closed, we can use the divergence theorem. And in some ways, this is a typical quick check that you can pretty easily see that we want you to use a divergence theorem, because you can see it's kind of messy, but the messy part involve parts that whose derivative is 0 once we do the divergence. Because what is the divergence of this one? So again, here's the P, Q, and R. So what is the divergence of this? It is, again, the derivative of the first one with respect to x, plus the derivative of the second term with respect to y, plus the derivative of the third term with respect to z. And so here you can see that is derivative of the first one is 3, derivative of the second one is 1, derivative of the third one is 4. In this case, the E is the solid upper half sphere. So again, by the divergence theorem, the flux double integral is equal to the triple integral. And like always, although this you might not know offhand, this then is equal to 8 times the volume. And now I'm curious. Does anyone know what the volume of a sphere is? Okay, very good. So in this case, we have 1/2 a sphere, so it'll be 2/3 times pi times 2 cubed. So whatever that is, 128 over 3 pi. Jeez. If you didn't remember the formula, well, we're getting the volume of a sphere, so we'd use spherical coordinates. So we'd have the 8 times the rho squared sine of phi. Rho would go from 0 to 2. Phi would go from 0 to pi over 2 because we're doing just the upper half. And theta would go from 0 to 2 pi. And you would get this same thing. Okay. It is early, so why don't I do the other one? So this is the basic one. Questions on this? Again, this is kind of a fairly typical test final question because it's using the divergence theorem, but once you use it, it's a fairly quick one. And as I said, these types of terms are fairly typical in that because it makes it look complicated, but with the divergence theorem, it goes away. So it's dissuading you from doing it the full way, because if you did the parameterization and plugged it in, we'd get something really messy. and you'd find out you don't really want to do that. So let me add on to this, which is here we did a closed one, but like Green's theorem, so the same problem as the last one, but now we're going to not have the disk at the bottom, so it's going to be an open half sphere. And I want to get the flow up through that. So let M be the open half sphere. Let D equal to the disk. And Z equals 0. And M prime equals the two together. And similar to Green's theorem, we know that if I do the integral of M prime, that's going to be equal to the integral of M plus the integral of D. So since we just got that the integral over is this, we just need to do it for D. And then we can subtract off. Okay, so like the last couple, again, the disk is a fairly simple thing since it's flat. So instead of having to get the partial derivatives and take the cross product to get the normal, you can just read it off, although you might have to be a little bit careful here. So what is the normal vector here? So here that it's the disk in the xy plane. So therefore, and we need the negative one because the basic flux is assuming we're pointing out. So pointing out in this case is pointing down. And so that means since I'm going to take the dot product of this with F, when I do this, I don't care what the first two terms are. And I know that the vector function, the last term was 4z plus 2. So I don't care what these are either. And I know z is equal to 0. So when I plug in here, I get, oops. Two. Whatever you want to call it, du, dv, whatever you want. And d here is the disk. I'll call it dA now, just to be different. And that again just means since it's constant, it's just negative 2 times the area at z equals 0. I think I said the sphere was radius 2, right? Is that right? Yes, okay. So therefore, the integral over the thing we want, the m, will be equal to the 1/28 third over 3 pi minus this, so plus. So similar to Green's theorem, it will sometimes make sense to close something so we can use the divergence theorem. And as I said, looking at the last one, in some ways, we often show that you want to use the divergence theorem by throwing in these extra terms that are complicated but go away if you get the divergence of the vector field. So any questions on this? Right, so I'm going to stop because that's mostly 4.6. So we have the one extra piece. So what's going to happen tomorrow is I will start by going over some of the homework in 4.5 and 4.6. So do more of those questions. And then we'll quickly start 4.7 and see how that's going. As I said, fortunately, I probably will not have your test back tomorrow, but I will have them for you by Monday. I will put up the answers later today. So any questions on this? All right, so the usual thing. So I'm going to stop recording, but if you have questions, stick around.